So this question is much more like the way you're gonna see, I would expect, you would see the, we call that Lagrange error bound on a Taylor polynomial, would be tested on the AP test. So this is the same problem that we worked on the other day. We made a Taylor polynomial for sine of x squared plus cosine of x, and you were wondering all along why this picture of the fifth derivative was there when they were asking you to make the fourth degree Taylor polynomial. Well, now we know. So let's say that we call P4 the fourth degree Taylor polynomial, the one that you made back in part C. Using information from the graph, show that, and then look at this expression they've given you. So it turns out that what's there inside the absolute value bars, the absolute value of P sub 4 of 1/4 minus f of 1/4, that's just another way of saying the error. When we saw it in your original set of notes, this is what we wrote. The absolute value of the remainder, the part of the Taylor series after the polynomial you used for your approximation. So just notice that this is another way to say exactly the same thing. P sub 4 of 1/4 is the result of using your fourth order Taylor polynomial to figure out f of 1/4 minus the actual value of f of 1/4. And we're not sure which one is bigger. One's an approximation of the other. We're not sure if it's an overestimate or underestimate, so we're taking the absolute value. So the absolute value of the difference between the two, or the absolute value of the error, we're supposed to prove that it's less than 1/3000. Watch. So it's that same formula we used there. We're going to try to make like what the next term in the Taylor polynomial would be. So we used the fourth order Taylor polynomial for an approximation, or they're saying pretend you did use the fourth order Taylor polynomial. So that required the fourth derivative, and it had x to the fourth in it, and it got divided by 4 factorial. So we're going to try to make the next term, which is going to have x to the fifth in it, and it's going to get divided by 4 plus 1, 5 factorial. Now the thing is that m, we're just going to have to figure out some sort of maximum for the fifth derivative on the interval 0 to 1/4. So I'm going to write a little note here that we're trying to figure out m. M is between 0 and 1/4. So this is a half. This must be a fourth. And so you don't have to be too nitpicky here. Feel free to use a round number. I see that 40 is definitely higher than the fifth derivative evaluated at 1/4. And that's an upper limit, all the way from negative 1/4 to positive 1/4. So I'm going to use 40 as my upper limit. So I'm going to try to write the absolute value of the fourth degree Taylor polynomial evaluated at 1/4 minus the real value of f of 1/4 has to be less than or equal to m, which is 40, over the next number factorial. So it's going to be 5 factorial times, that's a parenthesis. Well, actually it's supposed to be absolute value bars. This is going to be 1/4 to the fifth. Okay, so all I have to do is enough math to convince myself that that expression is, all right, so that's less than or equal to, what I'm going to have here, I'm going to have 40 over 120 times 1 over 4 to the 4th is 256. 256 times another 4, because I have 1/4 to the 5th. So I'm going to cancel those zeros. I'm going to cancel this 4 with that 4. And I know that that same error that I was trying to find has to be less than or equal to 1 over 12 times 256. I would come over here and multiply 12 times 256. Sorry, this is not the calculator section. So 256 times 12, if you think of a faster way to do this, feel free to. But pretty sure we're going to get a number bigger than 3,000. 1 over, oh, as long as you're convinced that that's more than 3,000, leave it like this, 12 times 256, which you could say is less than 1 over 3,000, because that denominator is bigger than 3,000, so the whole fraction has to have a value less than 3,000.